This is EE370. We are at lecture 26. So just to do a quick review, we are calculating the delay of the inverter. When the inverter whose delay we are calculating is driving, for now we have assumed that the load is also another inverter. So the inverter is driving another inverter. And for this delay calculation, we simplified few things. The first assumption was that the input being applied to this inverter is a step input. So this is of the form VDD into U of t. And we are interested in the delay from this input to this output, where the output voltage is going from VDD till VDD by 2. Right? We said that this delay is what we are calling as the propagation delay high to low, because the output voltage is going from a high value to a low value. Of course, the signal is going to fall till 0, but for the calculation of the delay, we need to know the time from this point till this point. And we said that this whole circuit can be modeled as shown below. So you will have a voltage source followed by R equivalent N, because you are looking at the discharge path and the discharging is happening through the NMOS transistor. Therefore, we look at the equivalent resistance of this NMOS transistor and some C total. So this voltage source will be of the form VDD into 1 minus U of t. The capacitor initially has a voltage VDD, and we are looking at the time it takes to discharge from VDD all the way till VDD by 2. Our equivalent N has been calculated as the average resistance for this variation in the voltage. Now we calculated and find out that the value of R equivalent N was equal to 3 by 4 VDD by I naught minus 7 by 12 lambda VDD square by I naught. The total capacitance C total, we broke this into two parts. There is a self capacitance, which is the capacitance because of this driver inverter itself, and a load capacitance or a fan out capacitance. So the fan out capacitance is being contributed by this inverter, which is acting as a load for our inverter. The value of C self is given by, so we have a CGD capacitance in both these locations, and we transformed the CGD capacitor as a single capacitor being connected from the output node to the ground. So the value was then given by 2 times the overlap capacitance into the width of the NMOS transistor plus the overlap capacitance into the width of the PMOS transistor, plus the diffusion capacitance. This is between the drain node and the bulk node. So the capacitance between these two nodes. This was given by the unit junction capacitance into the area plus the unit sidewall capacitance into the perimeter. Of course, this perimeter calculation does not take into account the sidewall on the side of the channel. The same thing goes for the PMOS transistor. So you have CJP into ADP plus CJSWP into PDP. The fan out capacitance is given by 2 times the overlap capacitance into the width of the NMOS transistor plus the gate to channel capacitance of the NMOS transistor given by COXWN into Ln, plus the same thing for the PMOS transistor, 2 times COVP into WP plus COX into WP into LP. Right? So all the parameters that you require for calculating the time constant is now available here. The time constant for this RC circuit is simply equal to R equivalent N into the C total. Then TPHL can be calculated as 0.69 into this time constant. So I got a very nice question from some of you about this calculation of the gate-to-channel capacitance of the PMOS transistor in the C fan-out. So let me quickly explain the question to you. Now we said that when your output at this node, let me call this as your out1 and I'll call this signal as the out2. So the question was the following: when your output here is going from VDD to VDD by 2, let's look at the region of this PMOS transistor. You will see that from VDD till VDD minus mod VTP, the PMOS transistor is going to be in cutoff. Now from VDD minus mod VTP all the way till VDD by 2, the PMOS transistor is likely to be in saturation region. Right? So we are assuming that the output is rising very slowly such that it can be almost assumed to be 0 here. Out2 is almost equal to 0, whereas the out1 has gone from VDD to VDD by 2. Out1 contributes to the VSG of this PMOS transistor. So the VSG of this PMOS transistor is basically going from 0 till mod VTP in this case. And then from mod VTP, it is going all the way down to VDD by 2. So the PMOS transistor will not remain in cutoff throughout this whole region. It is turning on, and once it turns on, it is going to be in saturation region because the VSD is very large given that out2 is very close to 0. Now the capacitance in cutoff region, so we are talking only about the gate to channel capacitance. In the cutoff region, this is equal to COX into WP into LP, whereas in the saturation region, we said that we'll model it as 2 by 3 into COX into WP into LP. So the questions I received were, shouldn't we consider at least the average of both these as the gate to channel capacitance contribution of the PMOS? This was one question. The other question was, is it likely that the transistor is going to be in saturation for the most of the time? This would be true if your mod VTP is much smaller than VDD by 2. If so, shouldn't we consider the transistor capacitance, gate to channel capacitance, to be this value instead of this? Right? Both of them very valid question. So let us first take a look at the expressions here. You can see that this factor COX into WPLP is already a small part of your C total calculation. Now the exact thing to do would be to calculate the amount of time where your transistor is in cutoff, the amount of time where it is in saturation, and then take the average of both these in terms of then you take the average capacitance in both these regions, right? You take the average of the whole thing. And now you can see that it is going to add a little bit more complications to our calculation, and think about how much benefit and accuracy you are getting by doing all of this, right? So it's not much. If you were to put the COX WP into LP here, you will make an error, but that error is expected to be a small fraction of your whole capacitance. So for a first order estimate, it is reasonable to assume that the transistor capacitance remains at COX into WP into LP. If you needed more accuracy, you are free to, maybe in your future projects, in your research projects, in your future designs, you are free to figure out how to take the average capacitance between average capacitance of both of these, and this is totally doable. But for a first order estimate, it is okay to make a small error here and then still get a decently good estimate of the delay. And you will also notice that because I have put COX WP into LP directly here, when you are dealing with a rising edge here, right? That means your input was a falling edge, you're looking at a rising edge here. You would end up with the same sort of confusion for the NMOS transistor, where the NMOS transistor would initially be in cutoff, then it can possibly enter into saturation region, and you would have to calculate your fan out capacitance differently for a rising edge at this node. But because we are making this approximation and using COXWP LP here, and assuming that the same approximation is being done for the rising edge, the value of your C fan out for now remains the same between the two polarities, right? Which means when you are dealing with a TPLH, the propagation delay from low to high, the only thing that you need to recalculate is your R equivalent. Instead of R equivalent N, you will do the calculations for the R equivalent P. The C total remains the same. So that does make our life a lot more easier. You have already done tutorials and you know the effort that goes into calculation of these, right? So it is much faster to estimate the delay if you have to do lesser number of calculations. Of course, we make a small error in the estimation of the delay, but as you can see, that error is going to be very much reasonable and very much okay for a first order estimate. So this is the reason why we directly use the expression COXWP into LP here. And for those of you who asked that question, a very good question indeed. All right. So this concludes our discussion for calculation of the R equivalent and C total for the delay. Now, if you, just for completeness, let me give you the expression when you are dealing with the low to high propagation delay. So in low to high propagation delay, this is your input is going from VDD to 0, which means your signal is VDD into 1 minus U of t. And the output node here is going from 0, and we are interested in the time instant till it reaches VDD by 2. And you will have some self-capacitance being offered by the inverter that you see here, and another load capacitance or a fan out capacitance being offered by whatever this stage is driving. Now in this case, because you are charging this node, you have to look at the R equivalent P of this transistor. Let me give you the expression directly. So R equivalent P will be also equal to 3 by 4 VDD by I naught minus 7 by 12 mod lambda P into VDD square by I naught. And the I naught here is the current that is flowing through the PMOS transistor in this direction when you are not accounting for the channel length modulation. So this whole term comes up because of the channel length modulation. The C total calculation remains the same. Therefore, your circuit now looks like this. So you have R equivalent P, and this is your C total. The voltage source will have a function that looks like VDD into U of t. So this node is initially at 0 volts, and from 0 volts you are charging this all the way till VDD by 2. And your tau P is simply given by R equivalent P into C total. The low to high propagation delay is now given by 0.69 into tau P. Right? Now, let's quickly look at what happens to your R equivalent when you increase the width and when you increase the length. I will do this quick analysis by assuming lambda equal to 0. Now, under these conditions, the R equivalent is given by 3 by 4 VDD by I naught, where your I naught, assuming short channel transistors, is going to be equal to mu n COX W by L into VD sat. So I'll assume an NMOS transistor for now, VD sat n into VDD minus VTN minus VD sat n by 2. Right? Now, as you can clearly see, when you increase the width of the transistor, your R equivalent N is going to reduce. Similarly, when you increase the length of the transistor, the R equivalent is going to increase. Nothing new here. This is what we expect. When you increase a width, you expect the equivalent resistance to reduce, or in other words, you expect more current to be flowing. Therefore, you expect your delay also. So your time constant is also going to reduce, or in other words, the propagation high to low delay is also expected to reduce. When you increase your length, the R equivalent is going to increase and your propagation high to low is going to increase. Now, here is a small catch in the statement, because you also know that when you increase your width, your capacitances can also increase. So, if I were to write it very cleanly, right, I can write your TPHL as 0.69, which is a constant, into R equivalent N into C self plus C fan out. Right? Now, let's consider this situation. And let's say this is driving another inverter. Now we are talking about increasing the widths of only these transistors. Now, if you were to increase the width of this transistor, right, then what happens is your R equivalent N is reducing, your C self is increasing, your C fan out is not changing because we have not changed anything associated with this inverter, right? Now, whether the total delay is increasing or whether it remains the same depends on the relative values of C self and C fan out. So, for example, let's say your C self is much greater than C fan out. I'm going to take the C self parameter outside. This will simply become equal to C fan out by C self, right? Where under these conditions, this parameter is almost equal to 0. It's much negligible compared to 1. Right, and under these conditions, as you keep increasing your width, this parameter is going to reduce, this parameter is going to increase, and effectively you don't see a benefit in TPHL. This might reduce marginally, right, but not significant enough, and it sort of saturates after a while. However, if your C self was much smaller, let's assume the condition where the C self was much smaller than C fan out, right? Then using the same manipulation, you will be able to write this as 0.69 into R equivalent N into directly C fan out. The rest of the parameters will be negligible. Now, under these conditions, as you increase your width, the R equivalent N will reduce and your C fan out is remaining constant. So now if your C self is much smaller than C fan out, then you will see that there is a reduction in TPHL as you keep increasing the width. Alright, so that is something you have to keep in mind. If you increase the width, of course, the equivalent resistance is going to reduce, but whether that directly leads to a reduction in the delay also depends on the total capacitance that you're seeing at the output, whether the capacitance is also scaling at the same time, which is why for every technology node, right, there is a minimum delay possible, because after a while, even if you keep increasing the width, the capacitance is also going to increase and you don't see any further reduction in the delay associated with it. Okay, so now there is one small aspect that we have not discussed, which actually affects your delay calculations, but we have not accounted for that in our model now. So let me quickly explain what that is. This is associated with the effect of CGD, and this results in an overshoot or an undershoot in your output voltages. right? So there is some capacitance that is because of the fan out or the load connected here. I'll directly call this as C fan out. There is another capacitance from this node to the ground. So this is all the drain to bulk capacitances. For now, I'm not including the CGD capacitance directly here. And I will show the total CGD capacitance between these two nodes. Now, this is of course the sum of the CGD capacitance from both NMOS as well as the PMOS. I'm showing it as a single capacitance here. Now, if you had a rising edge here, a signal that is going from 0 to VDD, you can see that there is this capacitance here where its one terminal is suddenly increasing from 0 to VDD. Right? So based on all the RC analysis, RC network analysis that you have done, you would expect that at the instant at which this change is happening, you would expect to see this node also to get pulled up, right? Some sort of capacitive coupling. Now, this is absolutely correct. You will have a small increase in this node, and let me show you how that is going to look like. So let's say this is your V in and this is your V out. Let's say this was the V in signal that you fed at the input. Now, without the capacitive coupling, you expect to see your V out signal to be an inverted signal like this. Right? Now, at the instant at which you see a sudden rising edge at the input, right? Ideally, we know that this capacitor is going to try and keep the voltage across it. It doesn't allow the voltage across it to change instantaneously. Now, if that happens, you would expect to see a rise here. Now, the problem is if the signal rises all the way till VDD, then of course this capacitor will tend to see a sudden jump across it. So the way how you can model this is, now at the instant where this sudden rising edge is happening, your transistors are not going to respond to that immediately, right? So you could model this as shown here. So there is some CGD capacitance and then another C capacitance. So this capacitance is between the V0 and the ground, right? So I'll directly show this as C total, but this is from V0 to ground. It is different from the C total we calculated earlier. This is all the total capacitance from this node to the ground without taking into account the effect of the CGD transforming it and adding it to the output, right? Now you can model it like this, and at the instant at which you have a rising edge here, right, you can now calculate how much is the overshoot you expect to see here. It depends on the relative values of the CGD and this C total between V0 and ground. Now, corresponding to this, so you'll see that overshoot appearing here, and then the transistors will kick in and then your signal will fall down, right? Similarly, when you have a falling edge here, you will see an undershoot here and then it will kick in. So your actual waveforms, if you were to simulate this, is going to look like this. So for every rising and falling edge at the input, you'll see a small spike and then it falls down. So this is a very interesting phenomena, and I would invite you to think about how the current directions are going to be in these regions. But of course, whenever you simulate an inverter, and if you don't see this sort of an overshoot and undershoot, either it means that your CGD capacitance is very, very small, or it could mean that there is something wrong with your transistor model or your simulation setup. Very likely the latter, because you expect to see some sort of small overshoot even if the CGD is smaller. So it's possible that somehow your model is not accounting for the CGD capacitance. And of course, not accounting for the overshoot and undershoot is also going to result in a small delay, small error in the estimation of the delay. but again, it still gives you a reasonable estimate when you want to quickly compare multiple designs, or when you want to quickly make decisions about what happens when you increase the width or length of the transistors in your design. But you should be aware of this phenomena, because in case your design has a much larger CGD compared to the load that is being connected from here to the ground, then this can become significant. Okay.